Greeting everyone. Here I present risk conditioned reinforcement learning and its generalization. Risk conditioned reinforcement learning is an extension of risk sensitive reinforcement learning. So the reinforcement learning agent, which makes sequential decision making based on the risk, receives a risk measure, the how to compute the risk and make decision based on the risk measure. Here we extend the kind of risk measures that an agent can receive to the any weighted valued risk. Weighted valued risk is a very general concept of risk measures, so it is wide enough to be applicable in real-world problems such as finance or self-driving scenarios. So let me introduce AAA conference. This is one of the best AI conference, H-index 254 and H5 median 463. Many important research has been presented. It has ranked Google Scholar fourth. There is no CVPL because CVPL is only focusing on the computer vision. If you include CVPL, it will be fifth. So it is also very important conference. Before we start, I will introduce our lab. Here is our professor, Woo Hong-wook, and he is big fan of embodied agent reinforcement learning and machine learnings. But actually, he is not so big fan of the risk-sensitive RL. So our lab actually researches such things. When human make an order to the clean up the table, then ChatGPT or LLM models translate into the instruction into small level so that an agent can easily understand the instruction. So it translates into to move the can to the trash, move left, move gripper down and grab such things, and the robot moves and clean up the table. So let me introduce the background reinforcement learning. Reinforcement learning is sequential decision-making algorithm, so it has wide of applications such as board game, chatbot, self-driving, or finance. Actually, RL serves the game-like environment. The game environment can be described by Markov decision process, MDP. So consists of four tuple. It consists of four tuple state. We observe something from the game. A action. We make some decisions. Then the environment changes according to the state and action. In this case, we do not consider the history, so this is Markov. Memory list is called Markov and gamma discount factor. So conventional RL algorithm is finding out policy pi such that maximizing the discounted sum of reward given state and action. So we are changing this objective from this expectation to the some other risk measure. So what is the risk? We make some decision making based on different utility rather than expectation. For example, we sometimes buy lottery. In this case, in worst case, we lost 5,000 won. In the best case, we can earn more than a billion won. So we buy lottery. That's why we buy lottery. But expectation is negative. Therefore, we call buying lottery is risk-seeking decision-making. We have a negative expectation, but in good luck case, we can earn lots of money buying lottery. We can consider the another case. For example, college admission. Students, you must have an experience of application submitting application for high probability of acceptance but less satisfying. This is called risk averse. But we call the risk as a quantifiable property. In this case, we cannot quantify the probability or satisfaction, so this is actually not a risk averse decision making. So let's formally define a risk. Risk measure is a function whose domain is random variable and whose codomain is a real number. There are types of risk: aleatory, a risk oriented by stochastic property, and epistemic, a risk oriented by lack of experience. We only deal with aleatory risk in this paper. As we discussed about, real-world problems are very risk sensitive. However, even in same application area, the preferred risk measures can be different and varying. Especially in finance, various risk measures are preferred, while classic risk-sensitive RL cannot flexibly adapt to such changes because we fix the risk measure before the training and it is cannot be changed. If we want to change the risk measure, then we have to train again. So let me introduce some popular risk measure, variance. Variance is expectation x minus alpha times a variance x. This is very simple, well-known, and popular risk measures, but sometimes the lucky cases are also accounted to the risk. The other risk measure is value at risk. Value at risk is quantile functions at alpha. Quantile function is inverse CDF, so only bad lucks are counted at risk. But the diversity, for example, ensemble, do not give any advantages. This is called portfolio diversification principle in risk measures, but not so important in this paper. This is generalized or version of the median. The median is value at risk when alpha equal to 0.5. 한국말로 하면은 퀀타일 펑션이 분위수예요. 뭐 100분위 이런 거 들어봤죠? 100분위랑 똑같은데 기준이 0부터 1 사이인 거예요. 그래서 뭐 0.25면은 4분위 값과 25% 분위 이렇게 하위 25% 분위 이렇게 생각하시면 돼요. So many risk measure has form integral 0 to the 1 time quantile function of x times some weight function phi. Here phi is some probability density on 0, 1, so it is always non-negative, and when we integral phi from 0 to 1 we get 1. For example, value and risk, we can consider the phi x as Dirac delta functions. We call such risk measures weighted value at risk. There are lots of weighted value at risk functions, and some risk measures variance does not belongs to the weighted value at risk, but lots of risk measures belongs to the weighted value at risk. So how can we obtain the quantile function? In previous work, implicit quantile network IQN, they proposed how to compute the quantile function of decision-making algorithm in RL. So we can use IQN algorithm to obtain the quantile functions. But this is not risk conditioned RL. And RCDSAC, risk conditioned distributional SAC. SAC is a name of RL algorithm. So first propose risk conditioned RL, but we have to fix the risk measure, and only parameter of risk measures are changes in RCDSAC. For example, they fix the value at risk, then only we change alpha. We cannot change to the some other risk measure. For example, conditional value risk. I made the risk. I extended the RCDSAC to the general risk measure, so I can change the risk measure from value and risk to the conditional value risk or CPW or whatever. So the main problem is how to encode and decode the risk measures. If we can encode and decode a risk measure, then we can do the same thing with RCDSAC, because in RCDSAC they only change the parameter. This is a real number, so encoding or decoding is very easy. But in our case, we have to encode and decode a function. This is very non-trivial, very difficult, because weighted value disk is realized by any probability measure on 0, 1. Suppose we solve the problem. We already solved the problem. Then a user can prompt to the agent. I want to conditional value this with confidence 25%. Then it will encode the risk measure and hands it to the agent. Then the agent will make decision making according to the risk measures. So we need some model which can encode the function and decode the function. The RL training is also straightforward. Risk proposal network, we named the solution which can encode and decode the risk measure, uh, risk proposal network. So the encoder will or decoder generate an embedding of risk measure, and the agent will roll out according to the risk measure. During RL update phase, the new risk measure is sampled. The risk-sensitive RL loss can be computed according to the newly sampled risk measures, so this is very straightforward. We sample the risk measure, update according to the risk measure, and roll out according to the risk measure. But we choose different risk measure when we roll out and update. This is just following the previous work and empirically tested. This is right way. So the solution must able to generate, encode, and decode risk measure. A model which is capable such functions are variational Bayesian model. Especially, we adopt adversarial autoencoder AAE for the model. This is one of the variational Bayesian model such as VAE. One of you might heard about VAE, so this is some model which can generate, encode, or decode. Then we must represent some data, the function, to able to feed the neural network vector form. In this case, quantile functions are better representation for the risk measures because it has more easy constraint. Integral to the 1 is very non-trivial, but in quantile form, only non-crossing functions are just required. And better space in mathematical sense. In quantile space, it has a good distance function, so-called Wasserstein distance, and compactness. This is not so important for the CSC, but this is important for the mathematical point of view. So we will represent the quantile function as a sorted points. Remind that function is a collection of points, x point and y point, because we are dealing with 0 to the 1 to the 0 to the 1 function. So we only need a point x, y. All of them belongs to the 0 to 1, and they are sorted because we need monotone functions. Here, the loss function can be defined as quantile regression loss and prior matching loss. The quantile regression loss is a special loss to estimate the quantile function. This is asymmetric L1 loss. Recall that L2 loss, MSE loss, is expectation matching, and L1 loss, or mean absolute error loss, MAE loss, is median matching. So quantile regression loss is asymmetric MAE loss, so it is estimating the quantile. And LW is adversarial loss corresponding prior matching. We need to generate some samples, so the encoding space must be follow some distribution. We will choose the 0 to the 1 uniform distribution because of the compactness, so we need adversarial loss so that encoded risk measures are exactly equal to the uniform distribution 0 to the 1. Then here x hat j is newly given quantile level for the reconstructions. This figure represents reconstruct risk measure and randomly generate risk measures of risk proposal network. Upper one is generated by cosine embedding in IQN. So this is not our work, but previous work. Down one is generated by our non-crossing quantile regressor. This is very clean, especially in the random. We take care about the random case because RL will be trained by the random case rather than encoded one. The encoded one will be only used in deployed case. So random one is important, and you can see in IQN the traditional one lost all its semantics because the tangent of the curve is semantic of the risk measure. However, in IQN it goes up and down, up and down, up and down, and up and down. This means the semantic of risk measure has been lost. To verify, we conducted an experiment in very simple toy environment. In this environment, risk-sensitive optimal actions are different and analytically known according to the risk measure. Without non-crossing quantile regression, an agent cannot solve such simple environment, but non-crossing quantile regressor, it can solve it. So the pink one is non-crossing quantile regression is absent, no non-crossing quantile regressor. And the blue one is with non-crossing quantile regressor. In this case, we know the optimal action and value, and the blue case can find out the optimal action and value, but pink case, it cannot solve anything. So we need a partially Boolton map because we are going to change the variable x to the y for the quantile function. So quantile function is inverse of CDF, and CDF is always non-decreasing. So this is partially monotone. Therefore, round y, round x must be larger or equal to the 0. Such constraint can be enforced by normalizing flow. This is a generative model which can be easily obtained at round y, round x. And we can constrain the round y, round x by normalizing flow. Especially, we focus on piecewise linear normalizing flow. We also mathematically proved that piecewise linear transform is enough to represent any risk measure with given any error epsilon. We will not introduce the formal statement or proof, but just remember that piecewise linear normalizing flow is enough structure. Non-crossing quantile regressor consists of three parts: a Gaussian quantile for the normalization, and piecewise linear transform for non-linear transform, and sigmoid for an output alignment to the 0, 1. Piecewise linear transform is a sequence of affine and Pirello transform. So affine transform is well known, some ax plus b form, but we will use sigma to prevent the duplication of notation. So this is sigma x plus b. Then Pirello is simply if x is larger than 0, it will be x, and if x is lesser than 0, it will be some sigma hat x. We evaluate the score of policy with respect to each risk measure. In our baselines are IQN, risk sensitive RL. The trained risk measure are equal to the evaluation risk measure. LCDSAC, this is restricted risk conditioned RL. The trained risk measures shares the parameter of the evaluation risk measures. GRIPS, this is ours, and evaluation risk measures are not never given when training. We evaluate our algorithm in financial tasks, especially stock hedge and stock on hedge. In this case, our algorithm shows computable even it does not given any information about the risk evaluation risk measure. Especially in stock on hedge, it even shows better score than IQN or LCDSAC. Also, self-driving tests, it is amazing. It shows dominant scores compared to other algorithms such as LCDSAC or IQN. We evaluate our baseline in donkey car simulation, and this is collision rate. Ours shows a very low collision rate, but it has tendency. It has increasing tendency, but IQN has so high tendency, so it does not show well, but it has also tendency. Then we have research questions. IQN can be considered an expert policy because it thought it is the risk measure is exactly given and evaluated by the risk measure. However, IQN is often shows less performance than GRIPS or even LCDSAC. We hypothesize that generalizing risk measures induces better exploration strategy. Therefore, risk conditioned RL shows better performance than risk sensitive RL. To verify the hypothesis, we conducted experiments in Mujoko environment. This is very well-known environment with some noise. This is deterministic, almost deterministic, so we injected some reward noise. The exploration is some strategy to find out better policy because we are interacting with the environment and obtain the reward and check. This environment requires more exploration according to the other paper, and this environment requires less exploration strategy according to the same paper. In this case, half zeta, which requires less exploration, GRIPS or LCDSAC with conditioned RL algorithm shows less performance compared to the fixed risk sensitive algorithm. Here, risk conditioned algorithms shows better performance compared to risk sensitive RL algorithm. So this gap explains risk without risk averse or risk sensitive case, the better exploration strategies are required. Risk conditioned RL shows better performance because of sophisticated exploration. Thank you for the listening.